Hi, I'm Mark Barsamian. In this video, I'll be talking about negating quantified statements. This content is from section 3.2 of our book, and it goes with these homework problems, which is homework H03.2. An important concept from a previous section is this idea that we had in section 2.1 was mentioned in the video for that section, and it was the idea that we're going to be discussing negations, and there is an issue of how to express a negation in a way that's clearest to understand. We'll always look for clearer ways of writing the sentence of a negation. We'll also be using a number of other concepts from previous sections. The idea of logically equivalent statement forms, denoted by this symbol. We say that two statement forms are logically equivalent if all possible substitutions of statements for the statement variables result in the same truth values for the statement forms. And we will be using De Morgan's laws. Remember that when you negate an AND statement, you get a new statement that's an OR statement. And when you negate an OR statement, you get a new statement that's an AND statement. And we'll be working a lot with conditional statement forms. Remember the conditional P arrow Q, which is also spoken if P then Q, has this truth table. The only time that if P then Q is false is when P is true and Q is false. In all other instances, if P then Q is true. In all those rows, if P then Q is true. And we'll be negating expressions that include conditional statements. Remember that the negation of the conditional statement, if P then Q, is this AND statement, P and not Q. Expressed on one line, we would write that this way. The negation of the conditional statement, if P then Q, is logically equivalent to this AND statement, P and not Q. So it's very important to remember that when you find the negation of a conditional statement, the new thing that you get, the negation, is a statement that is not an if-then statement. It's an AND statement. And we'll be dealing with expressions that involve sometimes the converse, the inverse, and the contrapositive of a conditional statement form. Those were introduced in section 2.2. So for this original statement, S, which is if P then Q, the contrapositive of S is this statement form, if not Q, then not P. The converse of S is this statement form, if Q, then P. And the inverse of S is this statement form, if not P, then not Q. In section 3.1, we discussed the universally quantified statement has this symbol, which is spoken for all x in D, P of x. And what it means is that the domain D has the property that every element x in the domain, when you substitute it into the predicate P of x, will turn P of x into a true statement. And we had this additional terminology that if there is an element x in the domain that when you substitute it into P of x turns P of x into a false statement, well, in that case, this universal statement would be false. And an example of an x in the domain that does this would be called a counterexample for the statement, for the universal statement. And finally, in section 3.1, we also discussed the existentially quantified statement, which has this symbol, which is spoken, there exists an x in D such that P of x. What it means is the domain D has the property that there is an element in D, at least one, that when you substitute it into P of x will make P of x a true statement. Our first example, we're going to discuss negating a universally quantified statement. And the statement is going to be this one, statement A. Every car in the Morton Hall parking lot is silver. The question is, what is the negation of A? Well, suppose that somebody said statement A. Somebody said, every car in the Morton Hall parking lot is silver, and you wanted to prove that they were wrong. What would you have to do? Would you have to go out to the Morton Hall parking lot and check every car and find out if that car is silver or not? No, you wouldn't have to do that. All you would have to do is go out into the Morton Hall parking lot and find a car, at least one, that was not silver. So the negation of that blue statement, the negation of statement A, would be this. The negation would be, there exists a car in the Morton Hall lot that is not silver. More generally, suppose you have a universally quantified statement. We'll call it statement A, and it's this statement. For all x in the domain Q of x. What's the negation of that? The negation would be this existential statement. Spoken, there exists an x in the domain such that Q of x is not true. Or you could say, there exists an x in the domain such that not Q of x. For example 2, let B be this statement. Every elephant at Ohio University is purple. Is this statement true or false? A lot of you would probably say, well, that's a false statement. But we should think about this as a quantified statement and express it in symbols. Okay, so we had the goal of expressing this statement B in symbols. And this is referred to in the book as writing the statement formally, just simply abbreviating the statement using logical symbols. So we introduced a domain called D. It's the set of elephants at Ohio University. We introduced a variable and with domain D, and we introduced a predicate, which is this sentence, X is purple. And of course, that sentence is neither true nor false until we choose a particular elephant to be X and substitute it in. All right, so that's statement B. What would be the negation of B? So in symbols, we see that the negation of B would be, there exists an X in D such that not P of X. So in words that is written informally, we'd say, there exists an elephant at Ohio University that is not purple. Now, think about this. What would have to happen for not B to be a true statement? You would have to have an example of an elephant at Ohio University that's not purple. Well, you can't find one of those. You're not going to find an elephant at Ohio University that's not purple. And so that means that negation B is a false statement. And since negation B is a false statement, that must mean that B itself is a true statement. Now remember, we've discussed this before. This idea of B being true is called vacuously true. The idea is that if your domain is an empty set, then anything that you say about the elements of that set is going to be a true statement, because for what you say to be false, somebody would have to give an example of an element in your set for which that thing that you've claimed is not true. So for this statement, every elephant at Ohio University is purple, if somebody wants to prove that that's false, they have to give an example of an elephant at Ohio University that's not purple. Now we're going to discuss negating an existentially quantified statement. We're going to let C be this existentially quantified statement. There exists a car in the Morton Hall parking lot that is neon green. And the question is, what is the negation of that statement? Well, suppose that somebody says, there is a car in the Morton Hall parking lot that's neon green, and you want to prove that that person is lying. Well, what do you have to do? You would have to go out to the Morton Hall parking lot and check every car and confirm that it is not green. So to do that, or to express in words what you would be doing, you would have to be confirming this. So again, to prove that this person is lying, you'd have to go out to the Morton Hall parking lot and check and confirm that for every car in the Morton Hall parking lot, the car is not neon green. So that thing that I just wrote down is negation C. So more generally, if you have this existentially quantified statement, the negation of that would be for all x in the domain not q of x. Now what about negating a universal conditional statement, like this one? For all x in D, if p of x, then q of x. Now I should have written that with parentheses, my usual way of writing quantified statements. So there's my statement D written the way that I prefer to write quantified statements, with parentheses around the predicate. So what would be the negation of D? Well, I'm going to suggest that we do this in stages. I'm going to start by writing down the negation symbol in front of the letter D. And then I'm going to put down the negation symbol in front of this whole expression that is the universal conditional statement D. Now remember that when you find the negation of a universal statement, it turns that universal statement into a there exists statement. We could think of this in pictures as moving this quantifier one notch to the right. So I want to move the quantifier one notch to the right past that for all symbol. So you see, we've turned that universal statement into an existential statement. There exists an x in the domain such that not if p of x, then q of x. But we should clean this up, because what do you mean not if p of x, then q of x? Well, here we have to use the fact that when you negate a conditional statement, the result is a new statement that's an and statement. So in this last line, I applied the negation to the if-then statement, and I got this new statement that is an and statement. Now, for example 4, let's let E be this universal statement, universal conditional statement that was introduced in the video for homework. Actually, I think this was H03.1. For all x in the real numbers, if x is less than or equal to 5, then x squared is less than or equal to 25. So let's find the negation of this statement. So you see that we did this negation in many steps. In the first step, we simply moved the negation one notch to the right. So that turned the for all quantifier into a there exists quantifier, and it put a negation in front of the predicate. And then in the next step, we negated the predicate. We negated this conditional statement form, and that resulted in this new statement that was an and statement. And then in the last step, we found the negation of this statement form, x squared less than or equal to 25. The negation of that is x squared is greater than 25. Now, for this example, which statement is true, E or not E? And explain. So here is statement E, and down here is statement not E. Well, remember that in the video for homework, this should be 3.1. The predicate p of x was this predicate. If x is less than or equal to 5, then x squared is less than or equal to 25. And we found that the truth set for this predicate was the following set. If any of these green x values are chosen and substituted into the predicate, they make the predicate true. But there are some bad x values out here, like for instance, x equals -7 has the property that x is less than or equal to 5, but x squared is not less than or equal to 25. So the bad x values are the ones out there to the left of -5. So because of this idea of the truth set not being the whole number line, we know that this universal conditional statement is false. And we'd say that the counterexample is x equals -7. There are many of them. Notice that the negation of this statement is there exists a real number such that x is less than or equal to 5 and x squared is greater than 25. Well, we have an example of a real number that does that. The number x equals -7 has the property that x is less than or equal to -5 and x squared is greater than 25. So the original universally quantified statement E was false, and a counterexample was x equals -7. And the negation of E is true, and an x value that demonstrates that that is true is x equals -7. Now for example 5, let G be this universally quantified statement. Every prime number is odd. Well, what would be the negation of this? Would be there exists a prime number that is not odd. Notice, to find the negation, we don't say every prime number is not odd. We say there exists a prime number that is not odd. So which of these is true? G or negation of G? Well, let's think about prime numbers. 3, 5, 7, 11, 13. Those are all odd numbers. Remember, a prime number is, well, let's see. What are the properties of a prime number? Prime number has to be a positive number greater than 1, and its only factors are 1 and itself. Well, so the only factors of the number 3 are 1 and 3. The only factors of the number 5 are 1 and 5, and so on. But wait a minute, there's a prime number we've overlooked. The number 2 is a prime number, and number 2 is not an odd number. The number 2 is even. So we'd say that the number x equals 2 is a counterexample that proves that G is false, or you could say that the number x equals 2 is an example that proves that the negation of G is true. Now, I want to revisit an idea we had in our last video. That is the idea of rewriting universal statements as universal conditional statements. Remember, the idea is, in this original statement, the domain was the set of prime numbers. We could think of that as being two qualifications, and we could spread those qualifications out. We could put some of the qualifications in the domain, and we could put some of the qualifications into the hypothesis of a conditional statement. That all sounds very, very vague, so let me just do it, and you'll see what I mean. So I put some of the qualifications into this quantifier for all integers x. So there's my universal quantifier, and then the predicate is this conditional statement. So how do we negate this? First of all, note that this is still statement G, just written in universal conditional form. So the negation of G would be so here we get to one of these points where we're going to move the negation symbol one notch to the right. So I'm going to move it one notch to the right so it goes past that quantifier. So that turns the quantifier into an existential quantifier. So here we have a universal quantifier. When I move that negation symbol past it, it's going to become an existential quantifier. So here I've just moved the negation symbol one notch to the right. I have parked it now in front of this predicate. Now I have to negate that predicate. So there exists an integer x such that x is prime and x is odd. So this actually means the same thing as the negation that we had on the previous page. There exists a prime number that is not odd. Now let's return to this universal conditional statement E that we discussed earlier. That was a false universal conditional statement. Let's write the contrapositive, converse, and the inverse of that statement. Now we've discussed the contrapositive, converse, and inverse of conditional statements. Let's go back up and look at that from the previous section. These things. We know what to do with a conditional statement if we want to form its contrapositive, converse, or inverse. But what about a quantified conditional statement? Well, the idea is that you do these things just to the conditional part. You don't do anything with the quantifier. So the contrapositive is going to mean, well, if we call this our P, and we call this our Q, this is of the form for all x in the real numbers, P arrow Q, if P then Q. So contrapositive E so I constructed for all x in R, the negation of Q, arrow, negation of P. Now remember that the negation of Q, the negation of x squared less than or equal to 25 is this statement, x squared is greater than 25. And the negation of P, the negation of this x is less than or equal to 5 is this, x is greater than 5. So there's the contrapositive. What about the converse? Remember, the converse of if P then Q is if Q then P. You just reverse the letters. So let me fill out that expression. So the converse is for all x in the real numbers, if x squared is less than or equal to 25, then x is less than or equal to 5. What about the inverse? The inverse, remember, the inverse of if P then Q is if not P, then not Q. So if I put in the actual expressions, it would be, the inverse would be for all x in the real numbers, if x is greater than 5, then x squared is greater than 25. So let's ask this question, which of those four statements, E, contrapositive E, converse E, and contrapositive E, are true and which are false? Well, let's go back up and review our discussion. Remember that E was this universally quantified statement, and we found in example 4 that E was false, because with a counterexample x equals -7. So we know that E is false. Now, we also know that the contrapositive of a conditional statement means the same thing as the conditional statement. They're logically equivalent. So that just leaves us with the converse and the inverse to figure out. So let's go up and look at those. The converse is this one, for all x in the real numbers, if x squared is less than or equal to 25, then x is less than or equal to 5. And the inverse is this one, for all x in the real numbers, if x is greater than 5, then x squared is greater than or equal to 25. We have to figure out if both of those are true or false? Well, remember that these two are logically equivalent. Because remember that the inverse is actually the contrapositive of the converse. It's not the contrapositive of the original statement, but the inverse is the contrapositive of the converse. So these two red circled statements are logically equivalent. So if we can figure out if one of these is true or false, then that'll tell us if the other one is true or false. Well, look at the inverse statement. It's actually the easiest one to understand. For all x in the real numbers, if x is greater than 5, then x squared is greater than 25. That's clearly true. So since the inverse is clearly a true statement, the inverse of e is clearly a true statement, we know that the converse is also a true statement. So of these four statements, the original statement E and its contrapositive, and then its converse statement and its inverse statement, of those four statements, E and contrapositive E are both false, and converse E and inverse E are both true. That's the end of the video. Thank you.